Hello, welcome to the series of annoying calculations in statistics. And today we'll be dealing with a hypergeometric distribution and talking about its expectation and its variance. And so just to remind you what the hypergeometric distribution is, the technical definition, and it's a discrete distribution. The probability that y attains an integer value, the random variable big Y attains the integer value little y, is r choose little y times n minus r choose n minus y over n choose n for y between 0 and the minimum of r and n. Now, just to remind you a little bit how this is often used, this is used in the situation, for example, let's say we have a urn, a container of, let's say, R red balls. And let's say big N minus R, let's say blue balls. And we want to know that what's the probability of getting exactly y, I'm sorry, of getting exactly y balls when one draws n, where of course n has to be less than big N, or less than or equal to big N, balls without replacement. And the understanding here is that the total number of ways to select small n balls from big N, well, that's the classic N, big N choose little n. And then the way you can get y balls, well, there's a supply of R red balls. The way you can divvy them up is R choose y. And then there are this many that are not red. And this is the number of ways of not getting the targeted red ball. So we'd like to, so this is the distribution itself. And what we'd like to do is we'd like to calculate the expectation of y and the variance of y. Now, how this is done, and I'm following our text, Wackerly Mendenhall, is that what we can do is we can take the n draws and divvy them up as follows. So imagine I'm putting the results of n of these. And for let's say the result of each draw can be either red, in this case, or not red. So what we'll do is we'll let xi denote the result of the ith draw. Okay. And then what we'll say is that xi will be 1 if the draw is red or the selected class, and 0 if otherwise. Okay, so that's for each one of these. So you've defined x1, x2, all the way out to x sub n. Okay, this is sometimes called a Bernoulli process. And then the y will be the sum from I equals 1 to small n, the number drawn, of xi. And so the first, so what we want to do is we want to calculate the expectation of y and the variance of y. And to do that, we need to calculate the expectation of each individual xi. So the first result we'd like to show is that the expectation of each xi will be, and this is going to be intuitive, it's going to be r over n. Now, it's not hard to believe that it's not hard to believe that, first of all, that the expectation of x1 is going to be r over n. That's pretty simple. And I'm going to do this inductively. Now and to show the induction, let's look at expectation of x2. Well, the expectation of x2, well, let's see what this is going to be here. Well, it's going to be the probability that x2 equals 0 times 0 plus the probability of x2 equaling 1 times 1. And that's what's nice about having these binary variables here. Well, this is now just the probability of x2 equaling 1, which can be broken down by a Bayes rule argument. x2 equaling 1, given that x1 is equal to 0 times the probability of x1 being 0 plus the probability of x2 being 1, given that x1 is 1 times the probability, x1 equaling 1. And now let's go ahead. So these are now conditional probabilities. Now this thing right here, this for x2 to be red, well, there still are reds left, assuming the first one was not red, but there's now n1 minus 1 balls to choose from. So that's his conditional probability here. And the probability this happening, well, there's n, big N minus r over n, because that's how many are not in the desired class divided by n, plus, now in this case, well, there's r minus 1 balls left because the first one draw was red. There's n minus 1 total balls left. And then the very first one we already said was going to be r over n, and it's just a simple addition. So it's going to be r n minus r squared plus r squared minus r n minus 1 times n. And then just doing a little bit of arithmetic here, the r squares cancel, and we have this r here, and we have this r here. R n minus 1 times n minus 1, which is just r over n. So that's true for the second case. And then the induction, so what we can do is I can assume that the probability, let's say, of xk equaling 1 is going to be r over n. And then let's show that the probability of xk plus 1 is equal to r over n. And it's basically a cut and paste of this argument right here. When we can write it down formally, that's going to be the probability of xk plus 1 equals 1, xk equals 0, probability of xk equals 0, plus the probability of xk plus 1 equaling 1, given that the probability of xk is 1. Sorry about the sloppiness. And it's identical, since these two things are the same as they were up here. So now that we know now we know the expectation of xk is going to be r over n, since basically it's just this right here, right? So now we want to do the expectation of y is now the expectation of the sum up to n, the xi, and we know the expectation is linear and there's n of them, which is the correct expectation for the distribution. Now, the fun starts with the variance here. And my assumption is that you know the following formula, and whose proof is really not that hard. But we're going to assume that you know that if you want to take the variance of the linear combination of ai xi, this is just going to be some xi's here. It's going to be the sum of each axi squared variance vxi plus 2, and then you're going to really take the sum of the what I call the non-diagonal entries. So the way this is done is 1i strictly less than j less than or equal to n, and we have ai aj covariance xi xj. Now assume you know that particular formula here. So that's how we're going to calculate, and the y, we're going to use this where y now is going to just going to be this. So each ai is 1, so these are all 1. So what we need to do is we need to figure out the variance and the covariance in order to make that work. So the variance of each xi, now we're back to our Bernoulli variables here, is the expectation of that squared minus the expectation squared. And this part here I'll do formally. It's going to be 0 squared probability that xi is 0 plus 1 squared probability xi is 1 minus, well, we already know what that is from up here, r over n squared. And this is, of course, going to be r over n minus r over n squared, which we'll find convenient to write like this. Now notice this, if you're familiar with the binomial distribution, this is a proxy for P, where the variance is NPQ. Well, n here is 1, a small n that is. This is a proxy for P, the probability of a success, and this is a proxy for Q. So this is highly intuitive also. So we now know what these terms are going to be. Now we should figure out what the covariance is. Now the covariance, let's do this in a different color. The covariance of each xi, xj, that's going to be the expectation of xi, xj, minus the expectation of xi, expectation of xj. Well, this is not going to be that bad. This part right here, each one of these is r over, well, I have to be careful here. is about, this particular thing. Each one of these is the same, so it's going to be R over N, quantity squared. This right here, though, is going to be a little bit of a different story. This thing here, this expectation, which I'm going to calculate here, xi, xj, well, what's going to be, it's going to be a probability, and the first probability will be the xi and xj, so 0, 0 times 0 times 0, plus the probability of this xi being 1, xj being 0 times 1 times 0, plus the probability of 0, 1 times the probability of 0, 1. Oops, 0, screwed that up. It's going to be 0 times 1, because 0 times 1, that's a times, not a plus. I mean, not a comma. And then we got the probability of 1, 1 times 1 times 1. So what do we have here? Well, this, of course, is a 0 because it's multiplied by 0, multiplied by 0, multiplied by 0. The only thing that survives is this. And we have the same old, same old. So assuming one of these, assuming say I is less than j or something like that, we're going to get r over n. Then with that removed, we're going to get r minus 1 over n minus 1. And then we're going to subtract. So that's going to be this part. So the total covariance will be r over n, r minus 1 over n minus 1, minus this r over n squared. And I'm going to write it this way. I'm going to factor out the r over n. Then I'm going to have the r minus 1 over n minus 1, right? And got a minus r over n. Get the old common denominator going. R minus 1 times n minus r times n minus 1. And the algebra is not too bad here. It's just a little tedious. But I have a Rn minus n minus Rn plus r over n times n minus 1. And let's post this up here. We're almost done with this little bit. Again, this is a covariance calculation. So we have this r over n. These two cancel. And then we have, this is an r. So it's going to be r minus n over n. Then we have the 1 over n minus 1, which will be useful a little later. R over n. Now I'm going to write this as r over n minus 1. But notice r over n is less than 1, so we'll just take this minus sign out. So this factor here is now positive. And we have this one here, which will be useful later. So that's a covariance of xij, right? So now what I'd like to do is I'd now like to use this formula right here. So now to get to the variance of y. And we're gonna do something here. We're gonna use this formula right here. This one. So remember, each AI is 1. So it's going to be the sum of the variances of the xi from I equals 1 to n. And then we have the plus 2 sum 1 I less than j less than or equal to n covariance x I x j. Now, keep in mind what this represents. With the 2, this represents the covariance for all. I will represent this as ordered pairs ij, where I is not equal to j, basically. And they're all going to be the same. They're all going to be this particular number there. So how many are there? Well, the way I look at it is if you look at these ordered pairs, we start 1, 1, 1, 2, that's all the way out to 1, n, 2, 1, 2, 2. I'm looking at all the order pairs. And then we go down to n1, n2, all the way out to nn. Well, notice there's n squared pairs, but then we have n on the diagonal. These things here are all on the diagonal. And those are represented here. So this thing here that includes a 2, and that includes a 2, what we have is we got these variances here, and there's n of them. And just remind you what they are. So the variance of all this is we have n times these. So it's n. R over n, 1 minus r over n. And then we have, in this case, minus, well, how many are these going to be? Well, it's going to be n squared minus n, which I'll write as n times n minus 1. So that, and then each covariance is, and I already put the minus there, so it's r over n, 1 minus r over n. And then we got this extra correction factor here, the 1 over n minus 1. And this is a big n minus 1. Okay. So that's going to be the variance of y. Now, notice we have this factor n, rn, and pq, and this. So it's n, r over n, n, p, q. Then we got our correction factor. So we have a 1 minus, then we have an n minus 1 over big N minus 1. So we got that, that should close it up, but that's usually how it's not how it's usually written. It's usually written this way. This correction factor, we'll just get a common denominator. So it's n minus 1 minus n minus 1 over n minus 1. And we're going to get the final glorious factor here. If I didn't run out of room, I don't think I did this time. It's good. So that finishes, after I finish this arithmetic, we'll be done. So the variance of y is n r over n, 1 minus r over n. So, and then we get the minuses cancel. So we get n minus little n here and n minus 1. And note, as n goes to infinity, this goes to npq, same as binomial. So that is what the variance of y is. Thanks for your patience, and thanks for watching.